In the final video in this series, we're going to look at the different lung volume measurements that represent different stages of inhalation and exhalation, as well as clarify some misunderstandings about lung volume and about how much air can and cannot be inhaled and exhaled by the lungs. First off, one thing that we need to clarify is that it is actually physically impossible to remove all air from your lungs during the natural process of breathing, and this is actually just due to the simple mechanics of how diffusion works. For example, if we talk about inhalation, during inhalation, the lung volume is going to expand, thereby decreasing the concentration of air within the lungs and creating a low concentration, also known as a low pressure system, while the atmospheric pressure and atmospheric concentration of air is going to be higher, resulting in air naturally diffusing in through the nose and into the lungs. Now, obviously, this doesn't happen indefinitely. Diffusion is going to stop when the concentration of air in the atmosphere and the concentration of air in the lungs is more or less equal. Now, if the air concentration, the ratio of the amount of air we have per unit of volume, is identical, that also means that the air pressure in the atmosphere must be approximately equal to the air pressure that exists within the lungs as well. And if we were referring to solute concentration, we would know this as isotonic. When we refer to air pressure, we use a different term, and that term is isobaric. Remember, the way to figure this out is by remembering that a barometer is the measurement device that we use to measure air pressure, meaning that isobaric pressure means that the air pressure in the atmosphere outside of your lungs and the air pressure inside of the lungs is equal. Now, in the event that 100% of the air actually left your lungs, that means that there would be no concentration whatsoever, meaning that the lung would deflate completely, and because there is no concentration gradient at all, because there basically is no functional volume of the lungs would not function, and this is what we call respiratory collapse, or simply saying that you have a collapsed lung. And this happens when the lungs get punctured, allowing the air to completely escape from your lungs, the same way that it escapes from a flat tire. And the only way that you can fix a collapsed lung is we would need to actually put a tube into the lung and allow air to be pumped inside, thereby allowing it to be reinflated. Now, if we look at the different volumes that are represented within the lungs at different stages of inhalation and exhalation, we can use this cute little animation to represent the different measurements of air that are taken in during inhalation or removed during exhalation, starting with the blue volume here. This is what we call your tidal volume, and of course the root of the word tidal is the word tide, referring to the natural movement of the ocean in and out due to gravity. Tide happens completely involuntarily and basically cannot be stopped, meaning that as long as you are alive and as long as your medulla oblongata is controlling your involuntary breathing, your lung volume is going to fluctuate approximately 0.5 liters during tidal inhalation and tidal exhalation, as long as you are doing involuntary breathing or passive breathing. Now, if you think about strenuous activity that requires a lot more oxygen than involuntary breathing can provide, obviously your lungs have the ability to inflate themselves to a greater degree, and the maximum volume that you can actually inhale during full inhalation is what we call your inspiratory reserve volume, meaning that if you were to fully inflate your lungs, as I am about to do now, and that, let's just call that maximum. What that means is that the difference between the tidal volume after I have involuntarily inhaled, the extra air that can be added on top of tidal inhalation, is what we call your inspiratory reserve. And again, this is quite important for athletes because they want to maximize the amount of inspiratory reserve that you have, because the more you can inhale, the more oxygen you can take within the lungs, and the more carbon dioxide you can output every time you exhale. Now, if we actually do the opposite, where we inhale fully and then exhale as much as you possibly can, as we've previously established, it is physically impossible to empty the lungs completely, so instead what we can measure is the maximum volume of air that can be exhaled after involuntary exhalation, which naturally is what we call your expiratory reserve volume. And again, this volume is quite important for any type of strenuous physical activity, because the larger your expiratory reserve volume is, the more carbon dioxide you would be able to push out of your respiratory system, which brings us to the final volume represented by the salmon-colored measurement here. This is what we call your residual volume, and the root of the adjective residual is the verb to reside, which means to live in. So this is the air that effectively lives inside of your lungs, and meaning that this is the air that remains in the lungs after a full exhalation has taken place, and this is the air that maintains a constant level of air pressure inside of the lungs and prevents your lungs from completely deflating, and thereby prevents respiratory collapse. Now, from these volumes, we can take a few additional measurements by mixing and matching the measurements that are listed. For example, if we take your inspiratory reserve volume and your tidal volume, so your inspiratory reserve and the tidal volume, and we're going to write tidal with a sub-I indicating that we're talking about tidal inhalation here. This is what we call your total inspiratory capacity, meaning that this is the total volume of air that can be inhaled through a combination of involuntary and voluntary breathing. Now, if we add the inspiratory reserve volume and the complete tidal volume, so all of the volume encompassed by tidal inhalation or tidal exhalation, and add this to your expiratory reserve volume, this is what we call your vital capacity. And anyone who engages in professional athletics activity, vital capacity is the most important measurement to gauge your cardiovascular health, because this is the total amount of air that can be exhaled after a full inhalation, effectively representing the total amount of air that can enter and exit your lungs, excluding the residual volume that, again, never leaves the lungs. Now, if we take your vital capacity, the total volume of your lungs that you can actually change through full exhalation, and add this to your residual volume, you can actually calculate what the total lung capacity is. Although calculating total lung capacity is actually relatively difficult, because measuring the residual volume of the lungs after full exhalation has taken place is relatively difficult to do. The only way that you would be able to do this is to measure the air pressure of your lungs when you have fully exhaled, and back calculate how much volume of air you have based on the air pressure that remains. So total lung capacity basically represents a theoretical measurement of the max volume of air that occupies your lungs after a full inhalation. Although, once again, this is relatively difficult to measure, which is why vital capacity is the most critical measurement for anyone who is curious or anyone who is looking to maximize their cardiovascular health. So vital capacity is determined by a number of factors, some of which we can't control. For example, your height. Your height is purely based on genetics, and this is simply because taller people have larger lungs, and therefore, because taller people have larger lungs, that means that the inspiratory reserve volume of a taller person is going to be much greater than that of a shorter person. Another location is another variable rather, Freudian slip there, is your location of residence. Now, what does this have anything to do with anything? Well, the location of residence, in other words, where you live, is going to affect what the air pressure in your home environment is going to be, because if you grew up at a very high altitude hometown, this is going to have different effects on your ability to inhale and exhale compared to people who grew up in a location that is close to sea level, and this will be something that we will explore in more detail later. And the final variable, the one that all cardiovascular athletes want to minimize, is obesity, which is basically a measurement of your body fat as a percentage of your total body mass. Generally, cardiovascular athletes want to decrease obesity as much as possible in order to decrease the amount of air that is required to supply tissues to their body, and the less fat tissue they have, the less air overall is required, because the heavier a person is in terms of their body mass, the more energy they need to expend in order to move themselves. And again, this is why cardiovascular athletes spend a lot of time cutting down on obesity as much as possible in order to maximize their vital capacity. So this concludes our series on the functions and mechanism of the lungs. To test your knowledge, you can take a look at this case study that actually emphasizes the difference in elevation and the difference that elevation makes in terms of breathing. Something that a lot of cardiovascular athletes do is undergo something called altitude training that allows them to train at places that are much higher than sea level. So see if you can use your knowledge of lung volumes and the mechanism of how diffusion of air works during inhalation and exhalation in order to answer the practice questions related to high altitude training below.